Session on forecasters, priorities, and improving S2S applications. We have 6 talks lined up. First amongst them is Dr. David Novak from the Weather Prediction Center. He'll be presenting on the NOAA Precipitation Prediction Grand Challenge, strategy and ongoing activities to improve S2S precipitation predictions. Without further ado, David, I've seen that you're online. Your presentation's up and visible, and feel free to take the reins.
Excellent. Thank you very much, Jason. And would love to be there in person. I was really looking forward to this. I came under the weather. Keep you all well. Precipitation absolutely is one of the key elements that is a requirement for forecasters, and one that we want to see improvement here in that S2S timeframe. I'll mention I'm a weather guy. You know me as a weather guy, but we have a whole team that goes across timescales with the Precipitation Prediction Challenge, all the way from minutes all the way to a decade here. And so I'm presenting on behalf of that executive team, including my co-leads, Jen Wan and John Tenov. So you've seen it, you've experienced it. The impacts of extreme precipitation are occurring across the nation and across timescales. We've seen it just even in this year with convective systems in Iowa, in the east with Ida in New York City, atmospheric rivers across the west, certainly drought, and I know the drought is currently on a resurgence across much of the US this month. We've seen record low flows on the Colorado and Mississippi rivers, which has huge societal impacts in terms of commerce as well as water availability. And then recently, with Beryl and Debbie, seeing these tropical cyclones. In just over the past 20 years, the nation has experienced over $300 billion in damages of direct damages associated with precipitation extremes. That's counting droughts and floods. It's not even counting tropical cyclones. And that has resulted over 1,300 lives lost, American lives lost to this event. And you all know that having those early predictions in advance, say 2 to 3 weeks in advance, understanding these regime changes is really important. This has been recognized by the congressionally directed Priorities for Weather Research report, highlighting the urgent need to accelerate our improvements in forecast. They cite that, unfortunately, precipitation forecast skill has not improved substantially over decades and remains one of the major technical challenges in atmospheric sciences. And from an equity perspective, poor prediction skill for flood and drought has an inordinate impact on disadvantaged communities. You're probably familiar with the image on the left here. The seasonal precipitation forecast skill has been pretty stable over the last several years. And we have, examples that have dramatic impact on society. This is from the late 2023 to 2024 time period, where California was in a historic drought. And then, of course, we had this amazing onslaught of atmospheric rivers that pretty much eliminated the drought. This was not that well predicted, say perhaps on the order of 2 weeks in advance. Some of the signals started to be highlighted there. And so I know that decision makers would very much like a greater advance lead notice on these kind of regime changes, for example. So the Precipitation Prediction Grand Challenge is NOAA's response and rallying cry to this challenge. And it is to capitalize on scientific and technological opportunities to provide more accurate, reliable, and timely precipitation forecast across timescales, so all the way from hours to decades, and with a particular focus here on the development and application of an Earth system prediction model. It's grand, I get it. That's motherhood and apple pie there, I get it. But it is so important, and it is strategic, and it is what we need for these urgent improvements to precipitation. Along the left here, we have organized across the value chain. So you'll note along the bottom here, we have research by improving process level understanding and modeling and improving precipitation predictability understanding. We know observations are critical to understanding what is happening and how that occurs. So research is the foundation. And then we know we have to translate this knowledge into our models. So in the upper left here, improving prediction systems for precipitation, and our services by improving products and applications in the upper right. And then, of course, it all starts and ends with the user to enhance and sustain user engagement. So we like to say users as the driver and research as the foundation. So it is grand, and we know that precipitation comes in all sorts of shapes and sizes across the nation. We have broken the problem down here into about 5 different efforts. One is the winter precipitation forecast for water management in the Western United States. This notably includes and supports the Subseasonal to Seasonal Report to Congress pilot project. Some of you might be aware that the S2S report back in 2020 highlighted and proposed 2 different pilot projects, one in the West and one in the central US. And we do feel this is at least partially working towards that pilot project aspect. We also have appropriations from the Water in the West project from FY23 and 24. And our real focus here is improving atmospheric river forecast. Initially, this has been focused in, say, the first 7 days, but we do know that, that obviously there's a subseasonal aspect here as well. The second aspect here, the spring and summer extreme rainfall and drought forecast in the central US. This is an effort to improve modeling of extreme rain from severe storms, as well as the onset of drought. And again, this would be in support of one of the other pilot projects that was proposed for the central United States. We've seen, the devastating impacts of tropical cyclone rainfall. In fact, over just the past 11 years, inland rainfall and associated impacts have become the deadliest part of landfalling tropical cyclones. 55% of deaths from tropical cyclones occur with the inland flood threat. And so it's vitally important to provide more confident predictions of the maximum rainfall location, ultimately helping prepare the most likely area for major impact. And then it's not just about the warm season, right? We know that 1 degree at 10,000 feet can be the difference between just a cold rain or a devastating ice storm. And so we know we need to improve our modeling of winter storms, including precip type and snow level, and to help with decisions. And then on the long time scale, back to the west here, to enable multi-decadal projections of water availability in the Western US. This has had congressional interest by connecting NOAA's climate projections and hydrologic models to better understand the controls of variability in the West. So these are our focus areas. It is ambitious, but we did want to break the problem down. Some of these are resourced, some of these are not. I did want to highlight how S2S really is a neat sweet spot. This comes from Bart et al. 2016. It's from across the pond, but I think it speaks very eloquently to the challenge and opportunity here of S2S. So there's different scales here, from a single reservoir or city all the way up to a various region. And you can note the time scale goes across the bottom here. And in the green here is just highlighting notionally our current scale. So, we do pretty well with highlighting, say, the daily precipitation forecast, say, in a river basin, across, say, out to maybe almost a week here. On the other hand, we don't do that well with, say, a single city. And in fact, I think it's clear and good that they highlight that in some respects, getting the single city's rainfall forecast a week out and beyond to a season is frankly probably unpredictable. But there is a sweet spot here where there's clearly user needs and where there is some predictability, where I think we're all focused here in this large, say on a river basin, say, a little larger, this is a European country, where we can at least push that out into, say, weeks to a season here. And I know that's a lot of our efforts. So we have been resourced through the Disaster Supplemental and Relief Act of 2022. And we've focused these resources across that value chain, improving understanding of physical processes, particularly in the Pacific and particularly with the ocean-atmosphere interaction. And of course, this has direct impact on S2S. Exploiting observations, we have had some investment here into the next generation operational global forecast system, so the GEFS version 17, which again has linkages to S2S. We do have 15 user engagements that are now teed up and beginning later this month across the nation to really dive into user needs. And then we're working on products and applications here, such as the urban rain rate dashboard, highlighting where stormwater systems may be overwhelmed by rainfall rates. I did want to highlight on the international stage, we also have the Global Precipitation Experiment, or GPEX. And this is really NOAA leading in an interagency and international way here, focusing on precipitation prediction, and particularly focused on the Pacific. So it's focused on these 4 phenomena in the center there of atmospheric rivers, thunderstorm clusters, monsoons, and tropical cyclones. And really the first initial and major effort here is in the tropical Pacific to better understand those processes and their downstream impacts in North America in that S2S timeframe. So those are our existing works here. I would say our ambitions, if you want to highlight it here, again, some of these resource, some of them more in ambitions. Again, GPEX is in the organizing stage here, and again, to build better understanding of the Pacific air-sea dynamics and how that could translate downstream over North America. And that's done in concert with our colleagues of national and international partners. I really do like this figure from Stanadale 2017 that highlights how the tropical Pacific is just so important to so many parts of the S2S problem. The GEFS and seasonal forecast system are really pushing towards, for example, better teleconnection aspects such as the MJO. We know data sets are so important, especially as we think about AI and machine learning. So curated data sets such as CORE, or helping with our AI and machine learning applications. And then I know CPC has been really successful here in some of the experimental week 3 to 4 forecast, as well as experimental flash drought hazards. And that's been terrific to see that investment in improved services. So there are PPGC activities that are bearing fruit today. I did briefly just want to highlight from our colleagues at GFDL, this is one example of focused on that S2S timeframe, looking at the MJO. And the European Center has done really well in this area. However, through some experiments with SPEAR, the GFDL S2S model, we've been able to mimic that and really getting an MJO forecast out to about 30, 35 days, depends on your anomaly correlation threshold. The important question was, well, you know, what did you do? How did you do that? And ultimately, it came down to having more realistic convective parameterizations, thinking about the evaporation aspects in these, as well as the shortwave and long-wave radiation aspects in these convective parameterizations. So I know there's other science being highlighted here throughout the workshop, but did just want to highlight this is one example of a PPGC-supported result. And then looking beyond, and again, thinking, you know, across timescales here, again, in that S2S timeframe, I really do think the Western U.S. precip extremes is one of the key areas here, thinking about atmospheric river aspects in the West, as well as specialized assimilation of observations. GPEX and our understanding of the tropical Pacific has been a key focus area on the subseasonal timeframe. And then on the very short time range here, thinking about rainfall rates and extreme rainfall rate predictions, thinking about, for example, the Warren forecast system and what that can provide. I'll just close with the fact that these extremes are not going to stop. National damages exceeding $1 trillion a year are certainly not out of the questions. Perhaps a typical year in the 1930s, or excuse me, the 2030s, is, you know, a series of atmospheric rivers. We've got drought in the Southwest. We've got, you know, a Harvey. Maybe we've got 2 Harveys in a given year. Fort Lauderdale event, an Ida event. I think you get the picture. The important aspect here is accurate prediction is a key part of the nation's resilience to these increasing extremes. And so that really keeps us motivated as a PPGC organizing effort across NOAA to really keep trying to move the needle here. So PPGC is a historic opportunity to improve precipitation skill. It strengthens and sustains the nation's resilience for precipitation extremes for years to come as we face these increasing extremes. We know there's no silver bullet. There's no one thing that's going to solve it all. We need to have an end-to-end investment across observations, models, and services. And we're really excited to help lead this effort, including those efforts on moving the needle on S2S. So I'll stop there.
Thank you, David. Very nice talk. We probably have time for one question if anyone's interested in stepping up to the mic. David, we're not getting any takers, so I think we'll just push forward with the next talk. Thank you again so much. It is a very difficult problem, precipitation. As a CPC forecaster, it makes me pull my hair out every time I try. So it's a good endeavor, this grand challenge, for sure. Thank you again. See.
Thank you.
So our next speaker is Zewdu Segele, and he is here to talk to us about hybrid statistical dynamical prediction of the Indian Ocean dipole. Ms. Zewdu, give me a second, I'll set this up for you. Yeah. Just use the arrows. All right, thank you. Thank you.
I first acknowledge my co-authors, Dr. Segele and Wasila Chow. Just to give some background, so the Indian Ocean is definitely important for that region, especially the Indian Ocean dipole, defined as the sea surface temperature anomaly difference between the west and the east, affects the October to December rainfall over the equatorial regions of Eastern Africa. The effect of Indian Ocean also extends to the monsoon regions during the summer season. Temperature gradient between the south and the northern Indian Ocean affect the monsoon. And when the waters are cooler in the south and warmer in the north, there is an enhanced precipitate rainfall in Ethiopia. So the objective here is to develop the SST prediction model using the canonical correlation analysis and assess the skill of the statistical prediction, and also to develop a hybrid statistical dynamical model and compare that result with the skill of that forecast as well. Just briefly, in canonical correlation analysis, we assess the multivariate joint relationship between given a predictant Y with n observation and the number of grid point variables Q, and a set of predictors X. The problem is identifying the correlation, the intercorrelation matrices among the predictant and the predictor, and identifying the canonical coefficients from the eigenstructure. For the canonical coefficient A, which is associated with X, and B associated with Y, and given the anomaly, the prediction equation as given by Glenn in 1968 is shown there. We can exaggerate the anomaly or the total original variables. So the predictors and predictants we use are the extended reconstructed sea surface temperature over the Indian Ocean, that is our predictant. And we have predictors, different ones, including mean sea level pressure, Sea surface temperature also is a predictor over the Indian Ocean, the Atlantic, and the Pacific. We also use the zonal and meridional wind and their fluxes as predictor. We have 7 models from NMMA, and we use their IOD and compare the result with those found from the CCA. We also used the ensemble, in addition to the raw, we also used the regress the ensemble mean to calibrate the NMMA IOD forecast, and created a hybrid forecast by averaging the CCA with the calibrated NMMA IOD forecast. So this is our prediction strategy. So what we did, we used the first 30 years of the 43 years to develop the forecast, to identify the predictors, and select the predictors and develop prediction model. And then we use that model, statistics, to predict the independent 13, 14 years in the future. So those are independent, not related with the model development period. So real-time forecasts are also developed every month by repeatedly constructing models from 1981 to 2010. Base period, increasing the model by 1 year. So this is only to create ensemble members for the statistical prediction. This is one example of the cross-validated correlation for model developed using a single predictor. So the correlation is between the observed SST and predicted SST that is independently forecasted. For the Pacific SST shown on the left, then the Atlantic SST, mean sea level pressure, Indian Ocean SST, and the zonal and meridional wind and their fluxes. Generally, so the rates are positive correlations and the blue are negative correlation. Generally, we see a positive correlation. The one thing that we noticed that the eastern parts of the Indian Ocean, the prediction is much reduced. And the Atlantic Ocean also does not have any signal or linkage with the Indian Ocean SST. If we increase the number of predictors, here shown the Pacific and Indian Ocean MSLP used as predictors to give the cross-correlated correlation shown on the right. Generally, the correlation increases, but still we have a negative correlation over the Indian Ocean. So as a strategy, we divided the prediction into 2. First, because the Western Indian Ocean is significantly predicted, we develop a prediction model for that region, and then independently predicted for the Eastern Indian Ocean as well, and combines the 2 to get the IOD. So the results that I'm showing here now will be on using that strategy. So this is a 1 month lead forecast for the CCA shown at the bottom and the individual NMME members, and their ensembles shown at the top row. So this is the correlation. What we see is that generally for up to from January to June, the forecast has little scale, largely negative, or 0.2 to negative. But starting from July, we can see that a 1 month lead forecast gives a stronger cross-correlated validated scale. The strongest correlation is during October. We see that in sampling, the NMMEs give a slightly better result, but statically, not much difference really between the CCA and the individual model. Here is the separate forecast of for October. This is again is the 1 month lead forecast. showing for Western Tropical Indian Ocean. On the left, what we see is the results of the CCA. On the right is the NMME result. On the top is for the middle Western Indian Ocean. The middle is for Southeast Indian Ocean, and the IOD shown in the bottom. So the blue is the observed, and the rates are predicted. And the correlation, cross-validated correlation is shown at top right of each box. Generally, the Western Indian Ocean is highly predictable, but the Indian Ocean, the prediction decreases substantially. The IOD is, however, is still strong. Comparing the NMMEs, we see the CCA has the lowest error or amplitude compared to the others, but in terms of correlation, it is still near comparable. The RMSE error is shown in the bottom there, and the CCA has lower RMSE, while the raw models have larger RMSEs. So the errors there increases. Here is the real-time forecast for 5 lead times. And the colors for CCA shown on the left and for the model and CCA shown on the right. So the colors are the different ensemble members created by simply varying the training period. And as we can see, the spread in the ensemble is not that high, indicating that the models developed for different periods are stable. The ensemble shown on the left is the red one, and on the right we are comparing the NMME. Now the NMMEs are regressed against the observation, so their error is also reduced. Their biases also are reduced. So the ensemble and the NMME are shown. The NMME ensemble regression is shown in cyan. And the ensemble, actually the regressed ensemble average is shown in blue, and the hybrid is simply the cyan plus the green average without any scale adjustment. And the CCA appears to give a higher value. We see now their scale here. So these are calibrated scales for the individual NMME members as well. So generally, the skills are higher currently for all NMMEs. The CCA, the maximum is about 0.92 here, and shown is also the persistent, which does not have any significant, is actually negative. It doesn't have any skill. And the hybrid shown on the top, it's more or less comparable with the ensemble. We can see also that the ensemble regression and the average simple ensemble have a similar scale, the same scale actually, because the adding and multiplying by number does not change the correlation. The RMSE are indicated there on the right. Again, the CCA has higher RMSE, so also the hybrid model there. Otherwise, the model now compared to the previous one that we saw, the NMMEs have now lower RMSE compared to +1 and above RMSE shown below, because they are now regressed and the error reduced. To summarize, so the Pacific SST gives the highest correlation. The Atlantic Ocean does not have any linkage with the Indian Ocean, and the CCA and NMME perform poorly in January to April, but they have a better skill during the fall and the winter season, and up to January, up to December. The CCA IOD skill is comparable with IOD obtained from the regression of an NMME, but the RMSEs are slightly higher. Much of this website contains much of the resources on Indian Ocean. Please have a look. Thank you very much.
Very nice results. We have time for a question. If someone would like to throw. Maybe a quick question for me. On one of your earlier slides, you showed the skill being highest in around October. I think you alluded to ENSO. Is that the reason why the skill is higher at that time?
Probably yes. Usually, for some reason, they have a higher skill during the winter season, where the variability is less in the tropical areas. Okay. That probably is one.
Great. Thank you again. Hi, Evan. Can you confirm you're online?
Yeah, can you hear me?
I do hear you. So I will stop presenting on my end, and I'll let you share your screen.
Okay. All right. Let me see if that'll work for me. How are we looking?
Yeah, we're looking good. It's in, if you can make it presentation mode, that might be helpful for us.
All right. Are we there now?
No.
Oh. I think I'm there for myself. I'm not there for you?
No, you're showing the PowerPoint view.
All right, hold on a second here. We're going to do entire screen, sir.
We can try.
And then let me know how that looks.
Yeah, I think,
There.
yeah, perfect. You got it. All right. So, all right. So let me introduce you real quick. So this is Evan Oswald. He's joining us from Ann Arbor, Michigan today. He's with the Climate Prediction Center, and his talk today, as seen on the screen, is the GEFS model's role in subseasonal forecasting of extreme heat at the Climate Prediction Center. Evan, feel free to take it away.
All right, I appreciate that, Corey. Yeah, so I'm a contractor at the CPC, and me and my federal manager, John Gottschalk, are kind of the main parts of that team that focus on extreme heat at the Climate Prediction Center. In 2017, as most people here know, the Weather Research and Forecasting Innovation Act focused the NOAA to look at subseasonal severe weather events, and it explicitly mentioned extreme heat events. So another thing that most people here know is that CPC is one of the leading operational long lead subseasonal forecast offices of extreme heat. And we do that through a product called the Week 2 U.S. Hazards Outlook, which comes out Monday through Friday. And it looks at next week's chances of impactful weather. We like to think of the WAWA map, so the front page of weather.gov. All those beautiful colors. Well, some of those colors are what we forecast really in that product. And the heat one, orange and like a magenta color, is specifically what I'm talking about today. Now, summer 2024, this summer is the second year of the key messages concept of product at the CPC. I know that other places have done it longer, but specifically, this allows us in that Week 2 Hazards Outlook product, when we see what looks to be a heat event, this kind of now gloms on a product for that event that kind of follows that event with lead time into the WPC. This is a pretty advanced and pretty new and really cool way to handle forecasting of extreme events. Now, we also have a Week 3-4 temperature and experimental precipitation outlook that I think we've had since 2017 maybe, but either way, inside that product, when we have a strong signal for excessive heat, or for example, there's a really strong signal in Week 2 and we're thinking about whether it continues. Now, there is sometimes an explicit mention of the heat in that prognostic discussion. And then I didn't actually put a bullet here, but there's an internal product that we've been working on now for the second summer, and that is looking at extreme heat specifically in Week 3. And our internal evaluation of how that's been going has actually been really positive. I'm going to talk a little bit about the ways, the products that GEFS is involved in for extreme heat forecasting and subseasonal. And I'm going to go kind of backwards to frontwards as far as longer lead time to shorter lead time. So the week 3-4 time scale is what I'm going to talk about here first. Is the we have, as you can see here, 3 dynamical models, GEFS, CWRF, and CFS, that drive this way to forecast extreme heat. The GEFS specifically ingests a reforecast, ingests forecasts from today, yesterday, and 2 days ago. We find that there's still skill looking a couple of days back even. And we're looking at days 15 through 30. We ingest variables 6 hourly maximum air temperature at 2 meters, and then 6 hourly instantaneous air temperature. And basically, we use those variables to craft a range of forecast metrics. And again, these are extreme heat. One here that was shown here in this top row is the probabilities of having either 3 or more or 6 or more days at the 92.5 percentile historical or greater. So that's that top 7–8% historically. And then you look across the ensemble space to get your probability. So 50% of the ensemble members say, we're going to have this situation that corresponds to your extreme forecast metric. That's what the probability is. Now, we do have a range of these kind of forecast metrics. That top one I mentioned is a probabilistic forecast. But if you look on the second row there, there's a deterministic forecast. So in other words, that's the ensemble mean of things like the number of days during the forecast period that hit, let's say, the 90th percentile or 100 degrees Fahrenheit. Now, we also have weekly averages. We did some averaging there because now at the week 3-4 time scale, you're looking a little bit more into that temporal averaging to get some of your skill back. And so, for example, we'll have like, what's the probability of week 3 being in that top 10% historically for the weekly average of Tmax or Tmean. And we do post-processing here at the week 3-4 time scale. We have the linear calibration. We also have bias correction for some of those deterministic forecasts. Let me talk a little bit more about skill, how they kind of stack up a little bit. I talked about those dynamical models. Those correspond to the various rows here. So dynamical models, CFS, ECMWF, GEFS. You saw these on the previous slide. And we also have some statistical models, which are on the bottom rows. And this is specifically looking at the probability of having 3 or more days in the week 3-4 time period with the daily mean air temperature being in that 92.5 percentile or higher. The columns correspond to different observational data sets. There's an internal one that I have labeled as Weishi on the left-hand side there. We have the CDAS, which some of you might recognize more as R1. And then on the right-hand side, we have the ERA5 analysis, which we have found to be a very helpful tool and a very strong reference. Now, inside of each cell, we have 3 numbers. You'll notice the first one is a decimal number, around like a 0.5, 0.6, and that is the AUK-ROC. The AUK-ROC is a skill metric that is really strong in evaluating the rare events, so tails. I won't talk about why it's better, but it's a good one. And when it's at 0.5, it basically is telling us that the forecasts we have here are as good as climatology. They're not really that helpful. And when they go up to a 1, they're perfect. So you'll see the numbers there, for example, for the GEFS V12 and the ERA5 analysis, we have a 0.639. Now, the next number to the right of that is in parentheses. That is a normalized version of that same AUK-ROC skill. In other words, when it's at 0%, it means it's as good as climatology. And when it's at 100%, it's a perfect prognosticator. So then the third number inside each cell on the right-hand side is the SETI value. And SETI is another skill metric that is really strong at forecasting things that happen very rarely. So like an extreme heat event or maybe a hurricane or something like that. But this is the maximum one over the range of forecasts of levels that you could choose from. And anyway, that number goes from 0 to 1. When it's at a 0, it's basically as good as climatology. When it's at 1, it's telling us that it's a perfect prognosticator. So you, in summary, you can kind of compare that number in parentheses to the right-hand number, the right-hand side of the comma, and those two numbers should be about what we're looking at. So like a 28% or like a 32% of the way from a not very good prognosticator or a worthless prognosticator to a perfect prognosticator. Those are pretty typical numbers at week 3-4 time period for extreme heat. Now you can compare that to the ECMWF above it, and it's much stronger. But I will warn you that those ranges of years that you've been using ECMWF and GEFS 12 are not the same. However, I've normalized them on this next slide. So this is from 2021 to 2023, which is the 3 years we've been using the GEFS 12. And you can see that the ERA, the ECMWF and the GEFS, at least according to the ERA 5, are really similar skill in prognosticating extreme heat. And we do find that to be the case. And, you know, I think that's a kudos, because I always thought the ECMWF was a very good model, and I'm glad that the GEFS model is forecasting about the same there. But one issue I wanted to kind of bring up here, I'm not going to beat it over the head a whole lot, but the truth is that when we forecast something in the tails, the district, and we want to do it in the absolute sense. So like talking about like the chance of reaching 95 during the forecast period in this particular area, let's say it's the Midwest or something, it can get difficult because of the differences in the higher statistical moments. Now, usually the mean is something that we kind of see almost tuned to between the models and the observations. But the truth is that the variance, the skew, the kurtosis, all of those things have a really strong impact on what the model sees the tails, the extreme heat. And these 10 panels on the bottom right-hand side, where I did this analysis a while ago, and it's actually the GEFS V10. But I will suggest to you that the GEFS V12 has the same issues. And that the top row is basically a histogram looking from the models. And the bottom is the same, but it's looking at the observed. And this is actually the Weishi data set there, so it's a little bit higher resolution. But what you're basically looking for, and this is summertime, 2 meter daily, it's a weekly average of the daily maximum air temperature. And it's 5 different locations from left to right across the US. It's May through September, 1999 to 2019. But the takeaway here is that we just have generally different shapes. They're not wildly different, but they're different. And different a little bit is a big difference at the tails. And so that is one of the tough aspects of forecasting extreme heat and probably other extreme, for example, precipitation was mentioned earlier, and I'm sure winds, this is also the case as well. So anyway, that's just something else. The figure on the top left is notable in that it is the bias, the historical bias in temperature as a function of the percentile that you're looking at. And this is fixed to look at DC area. And I want to say this is the CFS, not the GFS. But again, it's actually a pretty systems-wide thing. It's not specific so much to the GFS. But yeah, you can see that let's say the red line, which is the corresponding to June 22nd, it goes from a -2 or maybe let's say a -1 at those lower percentiles. But when you get up to the really high percentiles, let's say 90 and above, we're talking about a 1.5, 2 positive on the bias. So the sign change can happen. The bias changes as a time of summer, and it of course changes as a part of the country that you're in. So it can be pretty tough to post-process these things sometimes. I'm going to shift into week 2. So we also forecast specifically week 2. That's that really great product, the U.S. Hazard Outlook, and this is the kind of a tool that would support the forecast team that to make those forecasts. So we ingest again a reforecast base, and then
Evan?
Yeah, go ahead.
Sorry to interrupt. You have 2 minutes.
Okay, good. So basically, we have a lot of we ingest stuff here. We have forecast metrics here. We can calibrate and bias correct. We have again these skill maps. You can see that they're pretty similar, but so all right. So this is from 2017 to 2023. And basically, the ECMWF does a little bit better than the GEFS. Again, that's that right-hand side. But when we look at just 1 year, last year, we actually had better GEFS than we had the ECWS. Now, one thing I want to point out here, a couple things here. We do also do the National Weather Service heat risk product. Try to kind of estimate that, give our forecasters. We also look specifically at dew points sometimes. It's also, again, this really helps those forecast members understand what kind of conditions we're going to have in week 2. We have skill maps, but I want to forward here a little bit to this issue right here. I just want to touch on this real quick. This is 2023, and this is deterministic forecasting. This is looking at the maximum single day heat index value on the top and the air temperature on the bottom. And looking in that middle column, you see that there's a focal on the Iowa, Illinois area. Now, this particularly really threw the forecasters for a loop in 2023. And it's actually not specific to 2023 necessarily. It also exists beyond that, as this goes back to 2019 here. And basically, it's actually not so much a summer-wide thing, but just a monthly thing. When we scroll it down to just looking at July and August, on the left-hand side, that's the air temperature. That's that weekly maximum. In the middle, it's the heat index. And what you can see is that July and August, there's some pretty large numbers here. We got 8-degree warm bias, a 4-degree warm bias. And so that can be really tough for forecasters to use that. And so just to take away considerations here. I've already mentioned that those secondary statistical moments can be really important for us in extreme heat. I talked about the Midwest. You know, maybe it's fixed in your version. A couple things I didn't mention was just that some of our products do get post-processed using the real-time forecasting as opposed to the reforecasts. And this can be difficult because every couple of years we change our version. We sometimes kind of wonder if those post-processes help. Also, you know, we are looking at extremes, so we end up actually having to kind of reduce our sample size, right? So if we're only looking at that top 10% or whatever, it almost would really help. I know this is almost impossible. If we get a longer reforecast base, 50 years, I know that's insane, but that would be extremely helpful in the extreme heat forecasting field. And I'm going to leave it there. I know I'm kind of over time, but I really appreciate everybody for listening here today.
Great talk. Thank you, Evan. We will push on in the interest of time, but just a big thank you to all these tools and the large catalog of information you provide the forecaster. We all find it extremely useful. Thank you.
I appreciate you guys. Thank you.
Sure. If you don't mind, stop presenting. Okay, great. Okay, great. So next, I'm happy to introduce Lisi Pei. She's with the Climate Prediction Center and Earth Resources Technology. She's here to present on the development of a skill-based week 3-4 precipitation forecast consolidation.
Hi there, it's my great pleasure here to introduce some progress we made in the development of this scale-based week 3-4 precipitation forecast consolidations. So a little background about this is like CPC right now is issuing 2 categories, but we'll be transitioning into 3 categories soon. So as a supporting for that purpose and task, we are trying to do some research based on first guess consolidations to facilitate that process. I'll start by acknowledging all those invaluable contributions from all the co-authors in the list for their dedicated efforts and the critical insights brought into this project in the past few months, without which the progress we made would not have been possible. So this is what, if you go to the CPC website, week 3-4 outlooks, you will see a map like this for both precipitation and temperature. So using the norm defined as the 30-year climatology, what you see the color here is really a hint of how many confidence we have for those areas to be predicted either above or below normal. And equal chances there are indicating sort of a big unknown area with, for example, if we have 10 ensemble members, 5 of them saying, we think that's going to be above normal, and the other 5 says the opposite. So then a week 3-4 scale is, time scale is really hard for us to make a decision. So we place equal chance. And then that equal chance, you probably see a lot in those white areas in the outlook maps, which is unusual, and which is not unusual given all these uncertainties in this week 3-4 players on Earth system, which has been really highlighted and remarked in many previous talks. For example, simply just given MJO's uncertainty, like when you mentioned it yesterday, right? It's always kind of a slow phase development, but that thing in the week 3-4 over the United States can easily just lead to a flip of signs, of above and below for many of the regions. But despite all these difficulties, CPC does have a suite of toolboxes, both operational and developmental, to facilitate this forecasting process. Showing over here is examples of fundamentally it's 4 models that all these outlooks are based on. 4 dynamical ones, which are the ECMWF, JMA, the GEFS 12, and CFS V2. And on top of that, in addition to that, so we do have a very strong statistical model using the multiple linear regressions. So this model has been really well developed in CPC with so many different versions. So if you put, if we notice in this map here, it is the 2 category, so the color bar there, the white color is not existing. And that's where we're starting from there to just work on expanding, the probability forecast into 3 categories, and probably in the next few months or early next year. In this drop-down menu here, also providing to the forecasters are MOR I just mentioned. So right now, for week 3-4 and also at the monthly scale, we're using trend and MNGO as predictors associated with the anomalies we're looking at. And also, we have 2 consolidations routinely provided for the forecasters using both bias corrected and ensemble calibrated raw dynamic model outputs for this auto blend and manual blend. So the auto blend here is the fixed rate without gas over there, because back then I think it's still developing well. CPC is developing weights using the historical scores out of the other 4 ensemble members for this dynamic model forecast. But the forecasters does have their free option there to just on the forecast day which model they feel more confident on according to their expertise and experiences, so they can manually on the fly just do a consolidation. And this big box over there actually can open it up to, I would say it's really a suite of major projects and tools that instead of CPC that we're developing. It's really a Pandora's box and opens up to from developmental phase to semi-operational to operational, all kinds of statistical tools, bias correction model, calibrations, and studying to the regime change, connections, circulation pattern, biases, all kinds of things. And nowadays we're using progress very fast in machine learning consolidation tools. So those are probably, right now all kind of internal, but providing to the forecasters in their website. So these amounts up to almost, nearly 100, suite of tools. So it's really hundreds of pictures. We really want to browse through them. So that's tough because every Friday morning when this forecast is due, the first draft is due at 11 a.m., pretty much you only have 3 hours to make a decision. And this decision-making process could be tough many of the time, actually, because the models, they disagree and with conflicts. So for example, this is the forecast issued on July 26th, and thanks, Joanna, for showing this case study, in our last week's postmortem. So basically, you can see the dynamic models, they sort of agree on a wedding pattern over the South United States. Just a little uncertain on where is the cutoff between the normal wet, just above normal and below normal. Just the line there is not that clear. But with the bottom two models, we can see with that little uncertainty there, it matches just accidentally with the observed pattern pretty well, just for wrong reason. So given this, that brought up the importance thing, when model disagree and, there's uncertainties and errors there for sure, then if we don't have skills of them to bring, to land confidence from, will be really kind of out of nowhere. It's really hard to predict, or ensure the accuracy of a forecast. So shown here is really extremely fresh results that Corey conducted, and completed over, I think it's last week. It's really fresh and fun, our post-mortem meeting. This map shows like the total HSS score for all the forecasts CPC issued into this 2-category precipitation probabilistic forecast since 2015 September and till present. So typically, I think it's almost 463 on some like forecasts there. And generally speaking, the score is pretty good in the southwest United States, where relatively low precipitation, but the northwest and also on the Florida, the southeast, where the hurricanes visit often, those two heavy precipitation area, the score is pretty good as well. The most uncertain part of this map is showing us actually it's not unusual for the CPC forecasters to see, which is the Midwest, the Corn Belt, the East, and the Central United States. Those remain the hardest part for the week 3 for outlooks to strike accurately the precipitation. You know, I think probably the reason is kind of obvious because on this scale, the trout development, you know, the general circulations, the tropical highs and Great levels, low level jet, you know, Great Plains low level jet activities, those external moisture, all those things are kind of very uncertain or very hard for the model to agree on one pattern and put the trout right, put the convections right, the precipitation. So the scale over there is relatively low, but generally speaking, over all the time series, we can see majority of the time we do have scale above 0. That means like it's more than random chance. And in average, it's about 5.5, and majority of the time is in between 5 to 15% of hitting rate. So that's pretty good. But and also if we look into the reliability, you know, score, which means when we forecast with a confidence or probability of 55, for example, to 60% of chance, we think that's going to be above normal precipitation to occur. Actually, that black dot sits perfect on that perfect line there. So a perfect forecast will be just aligning well all along this red line, and the black dots there are indicating our forecast. So pretty much from 40 to 60% of the confidence, the forecasters, they do a really good job in the past 9 years, except being, when we're extremely confident and also when we're not that confident, we're a little bit too conservative. But overall, I think that's a good stepping stone for us to marching towards this transitioning into this 3-category probabilistic forecast next year. So to serve this purpose, this project here in the past few months is our job was mainly to score all the models, based still on those operational running for dynamic models. But, they post-processed into 3 categories. So now we just see some white colors in the map. And also MLR is also one of them, which is not showing. So 5 routine, those we consider as raw models, outputs. Yeah, although they're post-processed with bias correction and decalibration. And also another important tool that Corey developed is favoring this goal as well, which is the subsampling. So this subsampling is stemmed from, basically we score all those models almost, for example, out of all these 4 dynamic model outputs, we have almost over like 160 some members there. So some of them will do really well in week 2 because we're looking into week 3, 4. So week 2, by end of week 2, if we notice some models, they do really good. General circulations, 500 millibar pattern correlation with observations. So we pick them out. So the top 33 percentile of those ensemble members got picked out. And among those, how many of them are saying, hey, for this area, I think it's going to be above normal. For the other areas, I think it's going to be below normal or near normal. So those percentages are formed into this probability you see here. So using all these data, pretty much available since May 2022, roughly a little more than 2 years ago, we're able to make score evaluations of them. So showing over here is the internal webpage of your NOAA insiders with the access. You can see these products. So we've been doing both RPSS and HSS for all the raw 5 models plus 3 consolidations we've been done here. So for all the scores, it's been done 2 ways. For HSS, we're using the CPC conventional way, which is used for 3 category 1/3 as the reference line, as expected, like the forecast. And also we do conduct, the Wilks method, which is classic. When we compare one map to another map, we use observed frequencies to represent random chance. Basically, the joint marginal probability will be just by observation itself, not by just this 1/3. So that's the only difference there. And also showing here are only on the consolidations from those from the subsampling we just mentioned, and also 2 consolidations, which is kind of straightforward, equal weight, and those auto blend that CPC has been long time using. So generally speaking, the score over many of the places, almost half probably, I don't know, it just by, we're still under analyzing, it's pretty good, I think. And they are overall better than individual models. I think that's the key message we take from these preliminary results. And even in time series, it's the same story. And the consolidations better than the raw model outputs, and they about 7 to 8% of the hit to, just over the entire about 116 ensemble, the forecast members over here. Calibrated and bias corrected have their strength in either way. And ECMWF, yes, that's our superstar model. Almost all time we trust that, and we can see it's different yesterday. Sorry, I couldn't pronounce the name correct. Yeah, she introduced those thorough, pretty thorough, bias correction, and their AI models and calibrations into the whole forecasting time series. So we do see the score and the efforts over there turns out into the prediction scale. But overall, the samples, the subsampling, actually both spatial pattern-wise and time series-wise are very, very reliable, which means when we study into the physical links, we try to pick the good reasons for the forecast, and then we are heading toward the correct direction. So moving forward, I think, so we have so many things we can do for this consolidation. Based on the scale score we derived, we can do a 2D spatial sensitive, like weighted by each grid's historical scores, or we can use one score to represent all. Also, we can weight ensemble member size by their size, different contributions. Also we can use like their historical probability forecast anomalous behavior performance to correct their current probability forecast. So machine learning is a big player now in this field. So when I was drawing this Brahma map, it haunted in my mind all the time. Is like the less traveled. That's one of my favorite books. It might be the case in the past, but nowadays I think with all of us marching together in this direction, and so with so much more advanced technology, all kinds of new tools, I think it's coming with a better promise. So I stop there and thank you for your attention. And I think a lot of the authors in this work are in the audience here. So if you have any questions, feel free to reach out for any discussions or want to look at more of this course or whatever. So thanks again.
Thank you. Okay, so our next speaker is Guangwei Li from the University of Maryland. He's here today to talk about evaluating bias correction methods for enhancing summer extreme precipitation predictions in the U.S. Corn Belt using seawater.
Yeah. Hello everyone, I'm Guangwei Li. I'm a postdoc researcher from University of Maryland. I'm very excited to share my research on the DONG project. DONG project is supported by the USDA. It is aimed to help farmers to navigate the challenges from climate change and climate variabilities. And for some background, thanks to climate forecast system version 2, it provides 9 months predictions, and it runs 4 cycles a day, and so it's offering a large amount of ensembles. Although compared to version 1, the version 2 have a large improvements in temperature predictions, but it is still struggling on the precipitation. The CWRF, the climate weather forecast and weather research and forecast system model is expected to enhance the precipitation predictions because it has a flexible parameter scheme combinations, and the teammates have developed a new cumulus parameterization, which can reduce the dry bias in central US. Except of precipitation predictions, the CWRF simultaneously predicts the crop yields by it integrates the dynamic crop module. As correction, DCM tend to underestimate the heavy precipitations, and the heavy precipitation matters because the extreme events affect the agriculture yields. It may damage the agriculture, decline the agriculture yields, and especially for those heavy precipitation in these quantiles, there is a large bias there. So the bias correction, especially the quantile mapping based bias correction, is highly anticipated to address this problem. So the motivation is this study into ascertain the effects of applying bias correction to CWRF and evaluate the performance of bias correction methods on summer extreme precipitation predictions in the US Corn Belt. The stream flow is like this. The CFS provides the Poisson data to drive the CWRF, and 5 bias correction methods applied on the CWRF output. In this step, we using cross-validation methods. For example, in iteration 1, the 2012 is leave out as the test data, and the remaining 11 years is used to train the model, and then we can get the bias correction result for 2012. We repeat this iteration 12 times, and we can get this data set, which have the same dimension as CFS and the CWRF. The CWRF configuration. Poisson data is CFS version 2, and the spatial resolution is 30 kilometers. By the way, this is the domain of CWRF, and this area is a Corn Belt. So there are 19 ensemble evaluate in this study, and we using CFS version 2 initial at 06Z, and the model initial at May, April, May, and we use 5 days interval. Let's take a look at the summer mean precipitation result. This is the Riemann square error bias inter-analytical relationship of CFS version 2 CWRF and the bias correction results. As we can see, the CWRF enhances the precipitation, it reduces the Riemann square error a little, and the bias corrections for the reducing these errors. And for the bias, as we can see, the bias correction methods literally adjust the bias, but it's not good at inter-analytical relationship. Fortunately, we found the bias correction methods are pretty good at pattern correlationship. These 5 dashed lines are bias correction methods. We can see they have a higher score than CWRF and Novak. Let's take a look at the precipitation frequency and intensity. In this figure, the x-axis is the precipitation intensity, y-axis is the double logarithm of frequency. The black dots are observations, blue are CFS version 2, the orange are CWRF. As we can see, the CFS version 2 fit this straight line pretty well according to these equations, and we can see the CWRF reduce the overestimation of weak precipitation, and it enhances the underestimation of intense precipitation over 30 millimeter per day. And to check the frequency intensity of bias correction results, we plot this bias of double log of frequency plot. It's the distance between this line and observations. As we can see, the CWRF and the bias correction enhancing the reduce the frequency of weak precipitation, and the bias corrections, especially these 3 quantile mapping based bias corrections, they actually change the frequency intensity structure, and between when the intensity between 10 to 30 millimeter per day. And let's check the wet day and the total precipitation in wet days. This control plot is the wet day average across 5 years, and the bar plot and the key kernel intensity estimation plot is the wet day root mean square error of wet days. As we can see, the CWRF enhance this result. It reduces the overestimate of wet days, and it have a high, and the bias correction for the enhancing these simulations. And because of the overestimation of wet days, the total precipitation in wet days is also overestimated. And bias correction is reduce this bias a lot. Let's take a look at the R95 percentage. As we can see, the bias correction improves these indices a lot, so as the R99 precipitation, and this is consecutive dry days. As we can see, the CWRF can have a higher, a similar pattern like observations, and for the CWD, we can find that the bias correction improves a lot over the United States and the Corn Belt. But when it comes to RX1 day, we can see that we can find that the bias correction methods cannot show this show the low value area in these eastern US mountain areas. They cannot show this, and we can find from this KD plot the bias correction will deteriorate with the result, and something happens to similar thing happening to RX 5 days. And the intensity indices and R12, we can find that the bias correction have improved this a little. We average the root mean square error over space and subtract the observations, and then divide by the observations to get the heat map of relative root mean square error. The warm color means there is a deterioration. The cold color means there is an enhancement. As we can see, the RX1 day and RX5 days bias correction will deteriorate these 2 indices. And another thing we can find is the difference between various bias corrections is minor. It's the secondary factors. So conclusions, CWRF are moderately enhancing the predictions of time extreme prediction indices. In forecasting extreme precipitation events, the difference between various bias correction methods are minimal. Among them, quantile mapping reduces the bias of frequency when precipitation intensity between 15 to 25 millimeter. Bias corrections can significantly reduce the error in consecutive wet days, but will increase the error in RX1 day and RX5 days. It will slightly improve R95 percentage and R99 percentage, but will not helpful too much with consecutive dry days and indices. That's all. Thanks for your attention. Questions from the board?
Great presentation. So I saw like the bias correction technique, but your error correction is completely based on your random error correction, like routines or analysis, right?
Yes.
Yeah, so it will show any mean-related error, like a systematic error correction. So how do you, I mean, you cannot ignore the systematic error correction. So without systematic error correction, you cannot say like your model bias correct significant and just giving service.
Okay, thank you. Yeah.